Thank you, Andre. Yeah, it's a pleasure to be here. I like the organizers for the invitation. It's really a beautiful place and the weather is amazing. So it's fantastic week to come here. So yeah, I'm going to talk about some of the work that we are doing in Valencia on binary neutron star mergers, some recent work that we have done in this topic. Let's see. Okay, doesn't seem to. Okay, now. All right. So as I'm sure you will know, binary neutron star mergers are an excellent laboratory to study many different topics in physics, in particular involving string physics. So on the one hand, we have the gravitational-wave physics because it's one of the strongest sources of gravitational radiation. Also, nuclear physics is a perfect laboratory to infer the high density nuclear physics. I mean, the key to decipher the neutron star equation of the state of supranuclear matter and neutron star physics. Also to study gamma reverse and the physics of Tudor bits, because the central engine of this burst is supposed to be the merger of two neutron stars. And there is an association of this merger with the kilonovae, actually. Also, the nucleosynthesis of heavy elements and the kilonovae emission due to this decay, reactive decay of our process matter in the material that is ejected from the merger. And last but not least, also to study cosmology as a potential way to measure the Hubble parameter using gravitational wave information, in particular using DNS mergers as standard sirens. Now, all of this has, to some extent, already been firmly supported, let's say, with just one single not-imaginary observation we already have, which is the famous kilonovae, famous decay and detection of gravitation, DW 1708-17 with many electromagnetic follow-up observations. So I'm going to focus on the gravitational wave source aspects of the mergers. So before the merger, what we have is that before the merger, frequency is of the order of a few tens of hertz just before the merger, and below than 1 kilohertz. And that part of the signal is called the church signal. It's like a sinusoidal signal which increases in frequency and amplitude. And it can be treated semi-analytically using tools of analytic general relativity, like post-Newtonian approaches or effective Krakow approaches. But after the merger, we have to use numerical-relativity in order to extract the information on the waveforms. And that involves solving the Einstein's equations, the hydrodynamics and energy equations. We also have to take care of the magnetic field amplification. We have to take care also of supranuclear matter equations of the state, Newtonian emission, and so on and so forth. So the modeling, the numerical modeling of the post-merger waveform is currently the frontier in our studies of these kind of objects from a gravitational wave perspective. So our basic theoretical model for the systems comprises these different topics here. On the one hand, Einstein's field equations. We have long-term stable simulations currently to solve Einstein's equations with supercomputers. The most famous one probably is the so-called BSN approach to solve those systems. And we have also specific methods to actually discretize those equations. Thank you so much. Then for the hydro and MHC, we also have flux conservative hyperbolic formulations of those equations. And then with these two approaches, to these two basic building blocks, we also have to incorporate, all of this additional information like initial data that has to be eccentricity free, because most of these orbits that we study are quasi-circular orbits with no eccentricity. We can also include the spins for the individual components, and the spins do not have to be aligned with the orbital angular momentum, so we can have precession as well. We have to incorporate microphysics for the thermal equation of the state, magnetic fields, in particular for the amplification through magnetorotational instabilities, Kelvin-Helmholtz instabilities, and so on, formation of possible jets out from those objects. Dissipative fluids, this is the current frontier. Non-viscosity has to be incorporated probably in these systems, both bulk and shear viscosity. Transport of neutrinos, solving the full Boltzmann equations is still prohibitive from a numerical point of view, so there are approaches to solve those equations in an approximative way. And of course, nuclear synthesis. We also want to study the kilonovae. We want to study the process nuclear synthesis in these systems. And to do that, we have to couple those equations to nuclear reaction networks. So it's a very complicated problem from a physical and numerical point of view. So current simulations mainly deal with cold, zero-temperature equation of a state. Very few include thermal equations of a state. And very few include neutrino effects, dissipative fluids, and MHD. But there are some of those. All right. So the post-merger signal is an important part of the signal, which not always appears in this kind of mergers. So if the mass of the two components is above some certain threshold, the system may undergo formation of a black hole in a dynamical time, so prompt black hole formation. So in that case, this is the kind of signal that we have in the spectrum. Okay, so this is the first case, but then we have two additional cases which are very interesting from the gravitational wave perspective, which is the case where a transient object may form, which we call a hypermassive neutron star, or a slightly more long-lived object, which is also transient, which is called a supramassive neutron star. The hypermassive neutron star, the remnant is supported by differential rotation and by thermal gradients. And in the case of the supramassive neutron star, the final mass is sufficiently small that it can be supported actually by rigid rotation. And rigid rotation is something that is going to happen in the long run because of magnetic braking due to magnetic field amplification. So I am going to be discussing this particular object, the hypermassive neutron star that may form in some of these mergers. Now, if one looks at the early post-merger part of the gravitational wave signal that I'm plotting here, this is a simulation by Exeguilas and collaborator. This signal is divided in three phases. We have the chirp signal, the inspiral, we have the merger, and then we have all this part of the signal which has a smaller amplitude but higher frequency. And these are basically oscillations, merger oscillations of the remnant, okay, of this hypermassive neutron star that has been created. Now, if you look at the spectra of this signal, this is plotted here on the right, you see in the spectra, if you just look at the black curve, the black curve is the total spectrum, you see some distinctive peaks in the spectrum. And those peaks are actually associated with the oscillations of the remnant. The dominant one is the F2, so we have a triplet. This triplet can be identified in the gravitational wave spectrum in all simulations, and the dominant one is the F2 mode. The F2 mode is the fundamental, the L equals M equals 2 fundamental mode. This is a pressure mode, so the restoring force in this kind of modes is the gradient of the pressure. And then we have these F minus and F plus, which are quasi-linear combination modes. So these are basically linear combinations of the fundamental mode with this F naught, which is the quasi-radial mode associated with the rotation of the remnant. So future gravitational wave observation in principle could extract these two modes, the fundamental fluid mode and the quasi-radial mode. And if that were possible, then we could do astroseismology. Astroseismology with the post-merger remnant to constrain the equation of a state to infer neutron star properties. So this is the same, this would be something that would be very similar to what people routinely does nowadays to study the interior of the sun using helioseismology. So in principle, this is something that could be within reach in a few years' time. Why in a few years' time? Because the frequency is very high. The frequencies are of 2 kilohertz, of the order of 2 kilohertz, which is in a range of frequencies where our current network of detectors is not sufficiently sensitive. We have to wait for 3rd generation detectors, like the Einstein telescope, or the Cosmic Explorer in order to be able to detect those modes, those frequencies, and do astroseismology of hypermassive neutron stars. All right. I think I will use. Okay, let me then focus not on the early part of the signal. I'm not going to be focusing on this part of the signal. This is 25 milliseconds on the waveform, but I will focus on the late time of the signal. Why is that? Because when the two neutron stars collide, there is shock heating. And shock heating increases the temperature a lot, and there is a thermal gradient. And whenever there is a thermal gradient, you can have additional instabilities like convection. In particular, you can have convective instabilities because of the thermal gradient and entropy gradient. And if there is convection, you have two additional restoring forces. One of them is buoyancy, and the other one is the Coriolis force, because these objects are rotating very fast. If that happened, you could have additional modes at late times, and we were interested in seeing if new oscillation modes are appearing at late times or not. So to do that, we did the longest term simulations of binary neutron star mergers, up to about more than 100 milliseconds, 140 milliseconds in some cases, using first zero temperature equations of the state plus a thermal part. Those are hybrid models that I will explain in a minute. So, and yes, we found interesting new physics. So for the equation of the state, we were doing for those simulations something that is routinely done by a community, like the numerical-relativity community studying these objects. The equation of the state is split into terms. One of them is a cold part, a zero temperature cold part, and then to that part we add an ideal gas like equation of the state, which is thermal, to account for thermal effects. So for the cold part, we use piecewise polytropes. For depending on the range of densities that we consider, we have a different polytrope. This was an idea that was proposed by Jocelyn Red and collaborators in 2009 in order to fit the zoo of cold equations of the state by, different fits which are correct at different parts of the density. This is a pressure density diagram here. So you can have different polytropes with different pieces which are joined here in these points here. So this is what we are doing for the cold part, and then for the thermal part, in order to account for this shock heating, we use an ideal gas-like equation of the state with a gamma thermal in this particular range. Okay, so these are our models. So we have equal mass binary stars in quasi-linear circular orbits. These are generated using Lorem, which is a numerical-relativity code for initial data based on spectral methods, which is terribly accurate. It's very, very accurate. So we have two rotational neutron stars modeled by these hybrid equations of the state. We have these four equations of the state in particular. These are the properties of our models. And then for the evolution of these systems, we use an open source code, which is called the Einstein Toolkit, which is very often used by the community. Okay, so let me show you some of the results. So here, these are the spectra for different time windows. The two plots on the top correspond to the early part of the signal, and the two plots on the bottom correspond to the late time post-merger signal. As you can see in the early post-merger spectra, you see that the triplet that I was mentioning before. The F2 mode, this is the F2 inspiral mode, which is basically the F2 mode, and then we have the F2 minus 0 and the F2 plus 0 that I was mentioning before. Those are the frequencies here below, from 1 to 4 kilohertz. And then if you do the spectra of the waveform, you compute the spectra of the waveform at later times, you get this additional peak. So in black here we have the full spectra, and then at late times we have an additional peak that dominates at slightly lower frequencies. So what are those modes? Those modes were identified in our work with so-called inertial modes, which are due to convection, and they are restored by the Coriolis force. Those are similar to the famous R modes, slowly rotating neutron stars, which are axial led modes. So I'm showing here the results only for one of our equations of the state, but those results hold for all equations of the state that we discussed. And here are a spectrogram of those waveforms that I'm plotting here. This is the frequency on the vertical axis and the time minus time of the merger on the horizontal axis. You can see that there is this feature here, which is in the maximum of the spectrogram at a frequency of about over 3 kilohertz here, which eventually disappears. At about 40 or so milliseconds, the amplitude of that feature decreases very rapidly, and about 40 milliseconds, a new feature appears that actually supersedes the amplitude of the fundamental mode. Those are the new modes, the inertial modes that dominate at late times, these time of simulations. The good thing about those modes is that the frequencies are slightly lower. As you can see here, they are still quite high, over 2 kilohertz, but they are significantly lower than the frequency of the F2 mode. So in principle, it's easier perhaps to detect those frequencies with our detectors. So why are those modes? So in order to identify that those modes are associated to convective motions in the remnant, we can look at so there are different criteria to look for convection in a fluid. One of them is looking at the Rudolph frequency. Another one is looking at the sign of the Schwarzschild discriminant. The Schwarzschild discriminant is given by this expression here, and gamma 1 here is just the adiabatic index. So if this discriminant is positive, then the system is unstable to convection. If the discriminant is negative, the system is stable. So I'm plotting here, this is the remnant, which this is 40 kilometers across, and I'm plotting in brownish colors the regions of the hypermassive neutron star where the Schwarzschild discriminant is positive. I mean, where it is prone to convection. So initially, at early times, this convection appears in the outer layers of the remnant due to the shock heating, due to the merger itself. But at later times, this grows because of the thermal gradient. So it grows slowly, but eventually it grows to significant levels. And then convection dominates the entire remnant. So the good thing is that if we were able to detect these new modes that appear at late times, with gravitational-wave detectors, we could infer rotational and thermal properties of the remnants. And that's pretty interesting, I would say. So the early part of the signal, which is what we are detecting routinely with the LDK detectors, in particular for the kilonovae, for another detection that we have in 2019, is just the inspiral. And the inspiral gives you information on the equation of a state by using fits to the famous I love you relations, but that's part of the signal is for a zero temperature equation of the state. The equation of the state that I'm talking about is the finite temperature equation of the state, which is a completely different piece. So that information we don't have from the inspiral. That information we can only have from the post-merger signal. So can these modes be detected? Well, maybe. So we use one code which is called BaseWave, which has been developed in the corporation to detect those inertial modes. What we did was to inject those waveforms into Gaussian noise of second generation detectors and also the future Einstein telescope detector in different configurations. There is more than one configuration in ET. So we use BaseWave to reconstruct the signals injected into that noise. This is based on a morphology-independent approach, agnostic approach, using wavelets. And then we can compare. We can compute a quantity which is called the overlap, which gives you information about how accurate the reconstructed waveform is compared to the injected waveform. So we can infer those posteriors of the inertial modes. So, well, this is an example. I don't want to go through all of this, but so here I have different colors I'm putting here the injected under reconstruction time domain waveform at a distance of 5 megaparsecs. So, and here I have the spectrum, the amplitude of spectral density reconstruction. So, if you look at the black curve, is the red curve, sorry, this is the true signal, and then the blue, the shaded region here is the median reconstruction. So we have two different, so we have one sigma and two sigma, so 50% and 90% confidence intervals for the reconstructed signal, and this line over here in green, this is the part of the sensitivity curve of the Einstein telescope in this range of frequencies. So what we can see is that this is for the F mode actually. So no, sorry, this is for the inertial mode because this is the window where we compute the Fourier transform is in this late time part of the merger. So the region around the frequency peak of around 2.5 kHz is well recovered for very short distances, 5 megaparsecs. Remember that the 17017 was located at 50 megaparsecs, and this was already supposed to be a very close system. So as the distance increases, the reconstruction is much worse. So at 12 megaparsecs, we already cannot reconstruct the injected signal. So if we look at the overlap, here you have the expression for this overlap. It's just these inner products between these two complex quantities, the injected signal and the reconstructed signal, which is computed using this integral in the frequency domain. Basically, this overlap, the overlap is 1, then you have perfect agreement, perfect match between the injected and the reconstructed signal. If the overlap is 0, then there is no match at all. So here I have the network overlap of the late post-merger signal for the Hanford-Livingston Virgo detectors and for ET. This dashed line here corresponds to an overlap of 0.7. So above 0.7 is considered to be already quite good. So above 0.7 is something that in principle could be detected. And you see that for the current second generation detectors, the overlap is 0.7 up to a distance of about 1 megaparsecs, so very close. And for ET, the overlap is about 0.7 to a distance of about maybe 10 megaparsecs. So that's what we have for this type of signals. Okay, this is the peak frequency. We have something similar for the peak frequency. So, okay, those results were for zero temperature equation of states, for cold equation of states, but we know that the equation of state in the merger is not cold. It's not well approximated by a cold equation of state or by these hybrid models either, because it's not an ideal gas either. It's a microphysical equation of state. So recently we have done some simulations using finite temperature effects on the equation of state, and we tried to see if there were important differences with respect to the hybrid models. So the temperature in the inspiral phase, the temperature is of the order of 10 electron volts, which is much smaller than the Fermi energy, which is of the order of 100 MeV. Yeah, in the inspiral you can actually use zero temperature equation of the state. That's fine, that's perfectly fine. But in the merger, the neutron stars are hot, and shock heating increases the temperature to about 10% and 20% of the Fermi energy. So something like 10 MeVs. Then these finite temperature effects, the effects like the lepton fraction, the neutrino thermal pressure, and the neutrino cooling are going to be very important in order to model the remnant. And then you have to incorporate those effects somehow in the equation of the state. And this is what we have recently done. And the three main questions we are interested in addressing are those three here. Are the inertial modes that we discovered for zero temperature equation of the state still present in simulations using finite temperature models? And are they affected by thermal effects if they are present? Are thermal effects visible in the spectrum of the hypermassive neutron star signal? That would be very nice to see, because if it can give you a lot of information about the actual equation of the state. And what are the differences in the spectra of finite temperature models compared to piecewise polytropic models? So about 0.5 nuclear saturation density, so which is of the order of 0.16 per cubic Fermi, the gamma thermal, the adiabatic exponent of an equation of the state, strongly depends on the nuclear effective mass. It was shown by Lehman Hall in 2019. And then this hybrid approach based on piecewise polytropes highly overestimates the thermal pressure, so by several orders of magnitude. And obviously that will introduce significant changes in the gravitational-wave spectrum that we want to use in order to try to detect these effects. So to overcome these limitations, some simulations incorporate the thermal effect through full finite-temperature equations of the state. This was done some years ago, actually, quite some years ago, by using some approximation to the Einstein's equation using the so-called conformality condition. And in full GR, the simulations are much more recent, as you can see here. There was a first simulation by Shibata's group in 2011, but this is very recently that people are starting to do simulations incorporating finite temperature effects. The reason was that the codes were essentially crashing when trying to incorporate those effects into the modeling. But now the codes somehow work. So we are using this particular code, Illinois GRMHD code, which is also an open source code that you can download and use right away to do the simulations, which is based on the Einstein toolkit, but it's an improved version of the Einstein toolkit to handle finite temperature effects. So the tables for our equations of the state, microphysical equations of the state, are freely available at this website. And these are the models that we use. We have 4 microphysical EOS, slide 4, DD2, H-Shen, Latimer and Suez 220. Those are 4 of the most routinely used equations of the state routinely used in simulations of both globular supernovae simulations and binary neutron star mergers. So 2 of them are soft, and the other 2 are stiff equations of the state. So if you look at the soft equations of the state are slide 4 and LS220, and this DD2 and H-Shen are the stiff equations of the state. So you can see that the rate, so this is an existence plot. This is a gravitational mass radius diagram of different models with these 4 equations of the state. The solid line corresponds to this is the existence plot for these 4 equations of the state, and the dashed lines are the piecewise polytropic approximations that to those models that we also use. And you can see that for the soft equations of the state, it's like 4 and LS220, you can have much smaller radii than for the stiff equations of the state. And the 8 models that we are going to use are those identified by these red dots here, with a more or less constant gravitational mass in all cases. Okay, around 2.5, 2.9, something like that. Sorry, yeah, 2.5, 2.9. Sorry, this is not the gravitational mass. Here, it's here. No, this is the individual mass, 1.29, 1.25, something like that. Okay? So those are the models that we have evolved. Those equations of the state are, by the way, compatible with multi-messenger astrophysics observation. So those are constraints from NICER, from Newton, from DTAs, from the LBK as well. Here you have 1708-17, here you have 1908-14, which is a borderline case because it's still unclear if the less massive object is a neutron star or not, because it has a mass of 2.6 solar masses, which is a little bit in the very high range of masses. But those we choose those equations of the state in order to make them compatible with current observational constraints. Okay, let me show you a movie of 2 of these simulations. This is a quite complicated movie to visualize. So here, this square is divided into four sub squares, right? So in the top half, what I have is the results for the finite temperature model. Yeah, this tab means tabulated, okay? This top half of the square would be results for finite temperature model. The bottom half would be results for the zero temperature models, for the hybrid models, okay? And then the left part of the plot, I'm plotting the rest mass density, and here you have the scale of the colors, the palette of the colors. And on the right-hand side, I'm showing the internal energy, which we use as a proxy for the temperature. The higher the internal energy, the higher the temperature. Okay? Let's unmake this. So you see differences. If you look at the temperature, you see already differences between the tabulated model and the zero temperature and the cold models. So this is the post-merger evolution, by the way. It's not. I'm not plotting the inspiral phase. It's just the post-merger evolution. And at late times, you see that the objects, in terms of density, they look similar, regardless the finite temperature effects. But on the temperature distribution, there are some interesting differences. So if I look at those differences separately, if I first focus on the early part of the merger, of the post-merger, so 5 milliseconds after merger, what you can see here is, well, this cyan line here, which is difficult to see, is the boundary of the bulk of the hypermassive neutron star, which is defined as the circle, as the region where the density is of the order of 10 to the minus 3 times the maximum density. And then a few milliseconds after merger, like 5 milliseconds after merger, the production of heat, the increase in the temperature, is much more significant in the thermal EOS models, which is the bottom half of the panel. If you look at the top half of the panel. If you look at the temperature is much larger in the finite temperature models than in the piecewise polytropic models. Okay? But however, the density distribution is similar in both types of models. Now what happens if you go to later times? If you go to later times, 140 milliseconds, this is plotted here, you see that at late times the bulk radius of the hypermassive neutron star for the hybrid models is smaller. The hybrid models is the part below, the bottom half in both cases. These are two different equations of the state, by the way. So the bottom half. So the compactness is higher in those cases. And for both equations of the state, we even have like of the order of 10 kilometers decrease in the case of the Shen equation of the state. And then we have a ring of higher temperature. You see this ring here? Of higher temperature surrounding the hypermassive neutron star models in the case of thermal models. This is not so apparent in the case of hybrid models. So there are some differences that perhaps can be identified observationally. The most important difference is that since we have now additional sources of thermal support, we don't have just centrifugal support, we have also photons and neutrinos, we have thermal support and non-thermal support as well. The dynamics can be different, the dynamics of the remnant. So in particular, if we assume our simulation with the Latimer and Zesty 220 equation of the state, we found a very important difference. So here I'm plotting the lapse function, the minimum of the lapse function of the Einstein equations as a function of time. And you see, so the blue line is the zero temperature models, the black line is the finite temperature model. So the black line, the minimum of the lapse, reaches a value which is clearly not zero. So a value of the lapse equals to 0. When the lapse collapses to 0, we say that a black hole has formed. If you look for the horizon, and you can find a horizon. If the lapse is finite, small but finite, lapse equals to 1 would be Minkowski, let's say, and something between 0 and 1 would be, if it's finite but small, then you have a neutron star, okay? A regular spacetime. And this is what happened for a finite temperature model. However, for the zero temperature model, at some point the system collapses. So this is already a very important difference between the two models. We only found the formation of a black hole in the case of this equation of the state. How are the waveforms? Do they look any different between thermal models and non-thermal models? They do in some cases. Again, the blue line is the waveform, the blue line is the zero temperature model, the black line is the finite temperature model. You see that the amplitude in the post-merger phase, this is for the Einstein equation of the state, this amplitude of the oscillations of the remnant are much more damped in the case of finite temperature models than in the case of zero temperature models. Okay? That's going to have an effect on the spectra as well, and the detectability of these models. Of course, the black line is the most realistic model. Okay, so this is bad news in principle. Okay? For Hn is where we find the most important differences. For the other equations of the state, the differences are on the waveform are not so important. If you look at the peaks in the spectra, again, you see some shifts in the spectra. You see the appearance of the inertial modes, and you see some shifts in the frequency of the modes for finite temperature models, both for the fundamental, for the F2 mode and for the inertial mode. This will become more clear in a few slides. Now, if you have those spectra and you compute and you are able to distinguish those peaks in frequency, you will do astrocosmology. And there are many different groups that are trying to actually compute quasi-universal relations, that is, EOS insensitive relations, to fit those modes, the frequency of those modes with the log number, or with the so-called tidal deformability parameter. The second log number, I should say, okay, or the tidal deformability parameter. And this has been found for the F mode. So here are some references where this has been done. So these are the different, this is a spectrogram again. You have the different modes. One of them is the F max, that will be the maximum of the frequency at the time of merger. F2I is the initial part of the F2 mode. This F2 is the frequency of the F2 mode. And then we have the triplet, the F2 minus 0, the F2 plus 0, and so on and so forth. And here you have some of those empirical fits to those frequencies. Empirical fits with K2 kappa 2 is the second log number, which is also related to the tidal deformability parameter of the binary system through this relation here. This calligraphic C is the compactness of the star in geometrized units. Actually, I'm using G equals C equals 1 here in all these expressions. All right, so this can be fit. Here you have the empirical fits, and we can do the same with our thermal models. So those fits only exist for cold models, cold equations of the state, but not for finite temperature equations of the state. So we incorporated our models as well to those fits. So what you have here is the piecewise polytropic models are represented by circles here. And the finite temperature models, which are our models, are represented by triangles. And then we have additional piecewise polytropic EOS from Krakow in order to have a larger sample. And yes, indeed, you can fit the frequency of the maximum, the peak frequency of the merger, the maximum frequency at the time of the merger with the second log number, and it indeed follows quasi-universal relation for all of these equations of the state, also incorporating our finite temperature models. Okay? In fact, the STD, the standard deviation, the 1 sigma deviation for those models, when you incorporate, for those fits, when you incorporate the finite temperature models, is actually better than in the case of purely cold models. Not much better, but somehow better. And this can also be done for the other frequencies. I'm going to skip them. Okay, this is for the F2, which is the dominant one and has a very large amplitude. Those fits do not exist for the inertial modes because the amplitude is so low that we don't expect that would be possible to make those fits. But can we detect them? So we can use base waves as before and try to do the same. We inject the new waveforms and we try to reconstruct the waveform using base wave using wavelets, and we compute the overlap and see if we reach an overlap higher than before, lower than before. It's going to be affected, and we get something not very good. So again, we observe significant differences in the positions of the peak, in particular the shift to lower frequencies for finite temperature equations of the state. This is for zero temperature equation of the state. This is for finite temperature equation of the state. If you look at the values here, you see some shift to lower frequencies. In the case of the early inspiral signal, early post-merger. For the early post-merger, we get an overlap about 0.7. These are the 4 equations of the state, by the way, here. We have an overlap about 0.7 for all equations of the state except slide 4, even at a distance of 100 megaparsecs. So that's interesting. The F2 mode will be detected for sure. Well, with the Einstein telescope eventually. Up to a distance of 100 megaparsecs, the rate of binary mergers is quite high, and then we should be able to detect the F2 mode. Okay? What happens? Okay, this is the peak. This is the peak of the F2 mode. This is an interesting plot. This is the posterior probability distribution of the peak frequency of the F2 mode at different distances, 5 megaparsecs, 50, 100, 200, with different colors. For piecewise polytropes, the top row, and tabulated equations of the state, the bottom row. And the dashed vertical line is the injected value. Okay, the injected value of the peak frequency. And then the histograms is the reconstruction. So the more peaked the histogram is, the better the reconstruction is. Okay? This is happening only for H-Shen. So H-Shen shows the best results up to distances between 100 and 200 megaparsecs for both types of models. And what is interesting to highlight here is that there is an important difference between the zero temperature models and the finite temperature models. As you can see here, there is a 10% decrease in the location of the peaks in the case of the finite temperature models towards the smaller frequencies, which is interesting in terms of detection. Okay, we can do the same for the tidal deformability. Can we recover the tidal deformability for zero temperature models and for tabulated models? And again, the largest differences between these two cases are found for H-Shen, and it can also be detected up to distances of the order of 200 megaparsecs. So that's an interesting result. For the case of the inertial modes, the situation is much worse. Suddenly, we can reconstruct, we can get overlaps larger than 0.7 only to distances of the order of tens of megaparsecs instead of hundreds of megaparsecs, which happens for the case of the fundamental F2 mode. There are no significant differences between the piecewise polytropes and the tabulated models, despite the frequencies look so different. And yeah, so the overlap is of larger than 0.7 up to 10 megaparsecs only. And not for all equations per se, unfortunately. We can also recover the peak up to those distances, and again, as for the F2 mode, we have a 10% decrease in the case of finite temperature effects. We can also look at the detectability of thermal effects in these models doing Bayesian inference and doing model selection. Let me show you how we do that. The idea is the following. We get one of these waveforms with thermal effects for a given equation of a state. We inject that waveform into noise, Gaussian noise or real noise from the detectors. Okay? Now, that waveform is recovered with the same equation of a state using templates. And those recovery templates both include and omit thermal effects. Okay, in some case, we recover the waveform using non-thermal effects, waveforms, and in the other case, we recover the waveform using thermal effects waveform. And then we compute the base factors, and we compute the base factors in the two cases, and see which one is larger. Okay? And we claim detection if the log base factor is larger than 5 in favor of the thermal model. So we are doing model selection. We are comparing the model where the recovery is done using incorrect waveform because they don't include thermal effects, and a model where the recovery is done using correct waveforms including thermal effects. If this model comparison, the log base factor is larger than 5, voila, there's a detection. Okay? We use building, parallel building is a code for parameter estimation that has also been developed by the collaboration. So for each equation of a state and for inclination angle, we use fiducial sky location and distance. We compute the optimal signal-to-noise ratio of the injection across the grid of sky location and average. And we average, once we compute this rho, which is the optimal signal-to-noise ratio, we can compute the log base factor because it is proportional to 1/2 rho squared. Okay, we get a mean base factor. So the money plot is this one. Okay, well, this is the way we are doing the study. This is the evidence, the Bayesian evidence, which is the integral in the space of parameters. The parameters are the injected waveforms, by the way. We have the prior probability, we have the likelihood for all the parameters. So this is the likelihood of theta given a set of numerical waveforms. Okay, this is what I was just saying. Given two competing waveform models, N1 and N2, we compute the relative base factor given by this quotient here, and N1 is strongly preferred with respect to model N2 when this log of the base factor is larger than 5. And then what we do is we compute the minimum distance at which the average relative base factor between the thermal and the cold models satisfies this inequality. And this is what I'm plotting here. Well, okay, not yet. Remember, the waveforms can show significant differences. These are the comparison between the cold and the thermal models for each n, and this is the comparison of the cold and the thermal models for DD2, another equation of the state. In some cases there are important differences, and in some cases there are not so important differences. Okay? And this is the money plot. Yeah, let's look at this table. So this is the log of the base factor between the thermal model and the cold model for the 4 equations of the state. This is for an inclination of 0.3 between the plane of the orbit and the observer, and the distance in this particular case is 100 megaparsecs. You get values of the base factor larger than 5 in all of these cases. In some cases, in the case of Hn, significantly larger. And this is the mean detection distance in megaparsecs as a function of the inclination angle for the 4 equations of the state. The distance decreases with the inclination angle, but basically what this plot is telling you is that thermal effects in principle could be detectable with a log of the relative base factor larger than 5 at average distances of 50 megaparsecs for the inclinations of this smaller than 0.8, regardless of the equation of the state. Okay, so this is good news in principle, but this is for the future. This is something I didn't mention, is that this test, we have done this test using a very idealized situation where we are using an ideal free detector network composed of 3 cosmic explorers. So the cosmic explorer is the American 3-generation detector, the ET equivalent but in America. And we assume that we have 3 cosmic explorers, and we put them in the locations of LIGO, Hanford, Livingston, and Virgo, and we do this analysis. Okay, so this is just an ideal situation. Okay, if eventually we manage to have the ET and the 2 Einstein cosmic explorers, we should be able, in principle, we should be able perhaps to detect these thermal effects. How much time do I have?
Well, it's still 10 minutes.
10 minutes, that's right, because I have sufficient time to cover this last part. Okay, thank you. So the last topic I want to cover in this talk is something that we want to mention or warn the community doing binary universal simulations, because it's something that may affect the way the simulations are being done when the dynamics of the fluids is non-convex. So fluid dynamics and most of the astrophysical situations that we deal with and we model with our methods, and our methods themselves are in principle only valid to handle situations where the dynamics is convex, and functions where if you look at the other equations, situations where the fluxes are convex. If you don't have convex functions, then the methods may not work properly. Now, it turns out that in practice, when dealing with high density matter, with matter above nuclear separation density, in a natural way you can have non-convex thermodynamical effects appearing, in particular when you have phase transitions from hadrons to a quark-gluon plasma. In those phase transitions, you have lots of convexity. So the idea came about looking at this plot, and this result by Andy Valentine and co-workers, where they were studying different models of binary interstar mergers with different equations of state, and some of them incorporated phase transitions. So here you have the DD2 equation of state with and without phase transitions. If you have phase transitions, which is the green curve, you have that the peak frequency that I've been discussing all the time is shifted to a different value. Okay? This is the effective amplitude of the signal, and this is the frequency. And there is a noticeable shift in the frequency. Now these people look at these quasi-universal relations of the peak frequency with respect to the tidal deformability parameter, and they found that this quasi-universal relation was broken, didn't hold for the case of equations of state that had phase transitions. And those models are these green markers here. Those models are not in the fit. They are outside of the fit, are clear outliers. The thing is, how do we explain those outliers? So these people were claiming that is the fact that we have phase transitions was clear. So they use this result in order to say, if we have some models where the peak frequency doesn't fit doesn't fall in our fit, that means that in that particular system we have had a phase transition. I'm saying that that may not be true, as I will show you now. And this has to do with the convexity of the thermodynamics of the system. So the convexity of the system in classical fluid dynamics is determined by the equation of the state, and in particular by one quantity which is computed from the equation of the state, which is called the fundamental derivative, which is given by this expression here. So B is the specific volume, so 1 over rho, P is the pressure. All of these derivatives here are computed at constant entropy. This classical definition of the fundamental derivative can also be written in this form here. Cs is the sound speed, this gamma 1 is the derivative index, which characterizes the stiffness of the equation of the state at a given density. Now, the pioneer work on this non-convex thermodynamics was made by these people, Bethe, Saldovic, and Thompson, and the latter, in particular, Thompson introduced the concept of this fundamental derivative. If the fundamental derivative is negative, if a fluid has a negative fundamental derivative, that fluid is called a biceptive fluid. This may look exotic to some of you, maybe not, but there are, quite ordinary equations of the state, like the van der Waals equation of the state, which are actually non-convex. They have negative fundamental derivatives. And this concept of the classical fundamental derivative can be extended to relativistic fluid dynamics, and this was done by Jose Maria Ibanez and co-workers, and there is a slight difference in the expression. Now, this fundamental derivative measures the convexity of the isotopes in the zero plane. If it's positive, the isotopes are convex, mathematically convex, leading to expansive rarefaction waves, as we expect, we would expect, and compressive shocks, as we would expect as well. And this is the usual regime in which many astrophysical systems develop, okay, convex dynamics. However, some equations of the state may have regions where the fundamental derivative is negative, and the equation of the state is then non-convex. And then, if you look at the isotopes in the zero plane, we have compressive rarefaction waves, which is weird, and expansive shocks, which is strange. And this has been observed experimentally using transonic flows past air wings. You have regions where you have expansion shocks. This is very different to classical fluid dynamics. Does this happen in binary interstar mergers? It does. So as density is higher than M0, there is a phase transition into this quark-gluon plasma, and there are there's people that have studied these phase transitions, and they have shown that in this temperature range, in this crossover region, where the pressure is constant as the density increases, in this temperature range, the sound speed is non-monotonic. It's a non-monotonic function. And this non-monotonicity of the sound speed can also result from the behavior of the adiabatic index. And then if you plot here the adiabatic index as a function of the baryon number density, you see that it is not monotone. Okay? And this is plotted here for various equations of state used in simulations of Krakow supernova binary neutron mergers. That non-monotonic behavior introduces non-convex thermodynamics, and in turn it produces non-convex dynamics in the evolution of the system. So in particular, if there are phase transitions, this is always going to happen. There are always going to be regions of the P-row diagram where the dynamics will be non-convex. So what we did is to follow this work by Ibanez and avoid out and illustrate the effects of non-convex equations of states and the dynamics of binary neutron mergers using a toy model, a phenomenological equation of state that mimics the non-monotonic behavior of the sound speed or of the adiabatic index. So here we have two equations of state, FPS on the slide, and we have here our toy model, which is this green curve. Okay? Basically, it reproduces this non-monotonic behavior of the adiabatic index as a function of the density. And here, this is the relativistic definition of the fundamental derivative, and you can see that there are regions where it is negative. Okay? This is our toy model. Basically, we have an ideal gas where the gamma has been modified with this particular Gaussian profile, having this particular Gaussian profile. We have 4 free parameters that we can play with. Gamma 0, gamma 1, sigma, which is the width of the Gaussian, and rho 1, which is the floor density that we use. This is a toy model, but we just wanted to see if this introduces some effects before doing the real simulations using tabulated equations of the state incorporating phase transitions. Now let me show you something very simple. This is a blast wave collisions, two blast waves that collide using convex dynamics. So I'm plotting here the density and the velocity at a given time. So initially we have two blast waves, one from the left, another from the right, that collapse, collide in the center, and then they bounce, okay? And a shock region appears in the middle with zero velocity. So you have the zero speed in the middle, and then you have the shock region with higher density. So here on the left and here on the right, you have the initial states, okay? And then you have the shock wave moving to the left and to the right. This is the compressive shock wave that we all know. Now, if the dynamics is non-convex, these two same blast waves that collide in the center will develop this structure. We have the shock material at the center. This is a numerical artifact here, don't worry about that. It should be constant. Okay, so this is the shock material at the center with zero speed. Then we have the shock, but then this shock is divided. In the middle of the shock, we have an expansion. So this is an expansive shock. We have this sort of rarefaction here in the middle of the shock. So a shock plus a rarefaction plus a shock. This is a compound wave. This doesn't happen in ideal fluid dynamics. And the same is visible in the velocity here. This is going to affect also binary neutron-star mergers, not just these simple problems. This is a Riemann problem, which is trivial to study, but in a real application, in a real simulation, this is also going to appear. So this is what we did. We use a representative BNS simulations with this value of our parameters, and then if you look at the P-row diagram, you have regions in blue where the dynamics should be convex, regions in red where the dynamics should be convex from the classical point of view and non-convex from the relativistic point of view, green where the dynamics is non-convex, both relativistic and classical, and black is regions which are where the sound speed is out of bounds. Okay? So we use a model that is here in the green region, and we evolve. I'm finishing. If you look at this model here, this is the fundamental derivative of the density. So you see I'm plotting only negative values of the fundamental derivative which are values where this non-convex dynamics appears. So you see here this purple bluish region. At the center, where the density is the largest, is where you can have non-convex dynamics. So you will see in the simulation that this region doesn't disappear. That this region with these blue and purple colors is there during the entire simulation, even after merger. So it's a bit slow. Okay, after merger, when these two blobs collide, you still have regions where the dynamics should be non-convex. Now we look at the waveforms and at the spectra of these systems. What's going to happen? And we look at these relations, these universal relations, and this is my last slide. This is the set of models that we have considered, all of those equations of the state. And then we have in green here, we have the classical equations of the state, which should be convex. So these are all hadronic equations of the state, by the way. Then in red here, we have the outliers that Valencia et al. Show that do not follow the fit of the peak frequency with the lambda parameter. And then we look at our models with these two parameters, gamma 1, 3 and gamma 1, 3.5. Non-convex dynamics. You have that the models also go away from the insensitive, EOS insensitive relations that Valencia et al. Found. You can find models that apparently could be outliers, and they are not outliers because you have a phase transition. Not at all. Those models do not have a phase transition. They are outliers because the dynamics of the system is non-convex, and then it follows a different dynamics. You can have also universal relation for these non-complex systems. No problem. And in some cases, in some extreme cases, you can be very far away from this green curve. You can see shifts as large as 500 Hertz in some of the most extreme cases. Now the question is, these are results for a toy model. Do they hold for realistic equations of the state? This is something that we want to investigate. And this is my summary. So I have shown you some work that we have done in Valencia of binary crystal simulations, both based on hybrid models and thermal models. Those unveil the appearance of inertial modes which may dominate the spectrum at late times. We have tried to assess the detectability of those modes and of those thermal effects, and we see that the amplitudes and the frequencies are best suited for 3G detectors. The inertial modes can be reconstructed to distances of the order of 10 megaparsecs with 3-generation detectors. And thermal effects may be detectable to distances of 50 megaparsecs, again with networks of 3-generation detectors. And we have observed significant shifts in frequency for the F2 mode when the dynamics is non-convex, and this mimics these laws of universality when the equation of the state accounts for half and quark phase transitions. Of course, in the future, we want to incorporate additional physics like magnetic fields and neutrino transport viscosity to improve the realism of these simulations. But this is work for the future. And that's all. Thank you very much for your attention. Thank you.
Thank you for a very comprehensive, nice stuff. So, are there any questions? Yes, please.
The degree of freedom to be explored for constraints is the equation of state of Newton stars, of course. But to what extent is this degree of freedom degenerate with the possible modification of the general relativity? Could there be some confusion between the two types of degree of freedom, and to what extent?
Okay, that's a good question. That's an additional freedom that you have indeed. I don't know the exact answer to your question. That's something we're investigating, but remember that these objects are relativistic, but not so much relativistic in the sense that they are not black holes. I mean, gravity is strong, but perhaps not as strong in this regime yet, as in the case of black holes. Myself, I'm working in some models of modified gravity, but we have not yet done these kind of simulations. So I don't know. It's something to look at in the future, indeed. We're looking at the collapse of a neutron star to a black hole modified gravity currently, and also to the to the signal of the remnant of the black hole when you have modified gravity effects. But I don't know. I don't know if there is a degeneracy. Probably there is some kind of degeneracy. Again, this is something that one can use to test GR. I mean, an additional way to test GR perhaps in the future. I'm not aware of anyone doing a simulation using modified gravity. Well, that's not strictly correct. I think there is a group in Germany, the Tim Dietrich group. I think they are doing some simulations with modified gravity, if I'm not mistaken. Or GR was also accounting for the sonic fields for the dark matter colors of the models. But that's GR. So my answer would be that, yeah, there could be degeneracy. It's an interesting idea to study, but so far the community is not yet doing that. Because for the inspiral part of the signal, which is the frequencies that we have access to at the moment with the remnant detectors, GR is correct. As far as I know.
Thank you.
Okay, thank you very much.
I think there was another question.
Yeah, there was one.
Just a quick question, like, so when these inertial modes kick in, they kick in at some particular time. Does the gravitational wave memory effect can change these times when the inertial modes kick in, or this is independent, or they are not related to each other?
Sorry, I think I didn't understand you.
So the gravitational wave memory part of the signal, so you have the highest mode like L equal to 2, L equal to M equal to 2 mode, but there is some part of the signal in the gravitational wave memory. Okay.
Yeah,
And
the gravitational wave, if you look at the post-merger gravitational wave at late times in models, so when these inertial modes appear, you see some additional oscillations there in the time series. But they are tiny. The amplitude is very, very small. It's a challenge to detect them because the amplitude is of the order of maybe 3 to 4 orders of magnitude smaller than the amplitude of the peak frequency when the two stars merge. So these diagrams, these Crowley diagrams. So sorry, yeah. So if this is the amplitude here. So the initial amplitude of the fundamental of the Earth mode is up here, and the amplitude of the inertial mode is down here. Okay, maybe just 2 orders of magnitude in some cases. You see some effects in the waveform, but the effects are more clear in the spectrum. But given that the amplitude is much smaller, and given that the frequency is still quite high, chances are.
Okay, so thank you very much. Let's